Hi, everyone. I am going to talk to you about a new kind of function in the screencast. And if you look here at this function, you'll notice that this function is actually described in three different pieces, so to speak. Okay? Depending on the x value that you want to evaluate the function at, f of x will equal equal different things. So f of x equals 2x for values of x bigger than or equal to 3. For values of x between -4 and 3, not inclusive of 3, y equals negative x squared plus 1. And then finally, y equals negative x for values of x less than -4. Okay? Functions like this that are defined differently depending on the domain x, okay, because here what you see here is the domain when x is bigger than or equal to 3, okay, the range that corresponds to this domain would be looking at this y equals expression, y equals 2x, okay? And correspondingly, depending on the domain between -4 and 3, not inclusive of 3, corresponds to the output or the range of negative x squared plus 1. Functions like this that are defined in pieces, so to speak, depending on what x value you are concerned with, functions like this are called piecewise defined functions. Okay, they are called piecewise defined functions. And I kind of like I actually like the word piecewise defined functions. They're functions defined in compartmentalized pieces or different pieces depending on the domain. And what makes these functions interesting, and we'll look at a couple of really fun ones, okay? What makes these functions interesting is if you're asked to work with questions like A and B, okay, and C for that matter. So here, if I'm looking at evaluating f of 0, and I want to evaluate f of 0, well, f of 0 is asking me, when x equals 0, what will y equal? Well, when x equals 0, which piece of the function is relevant? X equals 0 is with this domain. So when x equals 0, I am looking at this piece of the function. When x equals 0, y equals 1, or f of 0 equals 1. Okay? F of 22, similar question. F of 22 is asking you, when x equals 22, what will y equal? Well, you have to find the relevant piece, so to speak, of the function that pertains to an x value of 22, and that is right here. F of 22 then equals 44. Okay? And of course, with everything we do in math this year and next year and the year after, math is just a story, right? Okay, I don't like, and we have not been, you'll notice, I don't like math being taught or learned in compartmentalized sections, because when you learn math that way, number one, you're really shortchanging the story of math, but you're also not appreciating the fact that everything in math that you learn ties in with everything else, okay? It's all connected in some way. So of course I'm going to ask a limit question here. This is asking you the limit as x approaches negative infinity of f of x. This is saying as x approaches negative infinity, what is f of x approaching? Let's see. Well, as x approaches negative infinity, what piece of the function am I thinking about? Oh, well, it's this piece right here for values of x less than -4, okay? Well, as x approaches negative infinity, y approaches positive infinity. So the limit as x approaches negative infinity of f of x is equal to just positive infinity. So here, if I were to think about what this graph f would look like, I know it's going to rise to the left, okay? I want you to notice something as well. Piecewise defined functions, I just happen to throw it up here where the pieces all happen to be polynomial, okay? And that is certainly not a criteria. I mean, you can have a piecewise defined function where maybe this is a sinusoidal function, maybe this is a square root function, Maybe this is a quadratic, okay? So the pieces, there are no restrictions as to what the pieces could be. All right, how about this one? What is the domain of f of x? Go ahead and try and think about this, looking at the function I gave you, and see if you can determine the domain. Okay, the domain here is all real numbers. X does equal all real numbers. In other words, there is no value of x for which the function is not defined. There is no value of x for which one piece of the function could not address the answer of what would the function value equal at that x value. And now we're going to sketch f of x. And this is where sketching piecewise defined functions could be kind of fun. Maybe fun should be in air quotes, but you get my drift. I'm going to do this reasonably accurately. Whenever I do something reasonably accurately, I'm going to kind of use my grid lines here. Okay. Okay. All right, well, let's try and graph f of x. So here, let's graph the first piece. Y equals 2x. Y equals 2x. I'm going to just go down here and preliminarily graph y equals 2x. Y equals 2x is a line with slope of 1. So y equals 2x is going to look like this. Oh dear. Well, okay, maybe I'm not so perfect after all. Okay, that's y equals 2x. And of course I know that it goes on forever, right? However, this function only applies for values of x 3 or greater. And in fact, when x equals 3, I know y equals 6. So I'm going to go back here to my graph. When x equals 3, y equals 6. So this is the point 3, 6. And I now know that this graph of this function, of this piece of the function, looks like this. Take my eraser now and erase, okay, that part. And what's important, I want to do this, I'm going to make sure this hole right there, that is a filled in circle, a filled in circle. All right, let's graph the rest of f of x. Let's see, the second part was negative x squared plus 1. Okay, this is going to be the parabola, y equals x squared, reflected over the x-axis, moved up 1. All right, I'm going to do that now. Sketch it out. And I've got this going on. Okay, now I'm going to check my domain. Let's see. Only for values of x between -4 and 3. Well, let's see. When x equals -4, y equals -15. And when x equals 3, y equals 10. Okay, so that means 3, 10. Okay, so 3, -10. Open circle, because this part's not inclusive. And then it goes, this function applies, is relevant all the way to -4, -15. All right, so this is the point 3, -10. This is the point -4, -15. Notice again, very important, open circle, closed circle, okay? And if I were to ask you, boys and girls, if this function passes the vertical line test at x equals 3, the answer would be yes. At x equals 3, y equals 6. At x equals 3, y does not equal -10. I'm just labeling that point so the reader knows that that is not, oh dear, well this just looks atrocious, oh my goodness. All right, and I know this big circle looks so silly, but you get my point. Okay, I'm going to go ahead and graph the last piece. Y equals -x. Okay, I know what y equals -x looks like, and maybe here I'll be a little bit more quick. Okay, y equals -x. I'm going to just look at my pencil point. Y equals -x looks like this, right? But y equals -x only applies for values of x less than, is it less than or less than or equal to? Less than -4. So I've got this. When x equals -4, right? y equals positive 4. So there's going to be an open circle. Oh my. It's going to look like this. Okay, and of course that would be through the, okay, so this is not perfect. And here you see, boys and girls, this is the entire picture here is the graph of f of x, okay? Notice in this case, notice a couple of things, right? In this case, the graph of f of x is here, f of x is discontinuous. F of x is a function, but it is discontinuous, right? In order to trace the entire function, you would have to pick up your pencil. That makes f of x a discontinuous graph. Are all piecewise defined functions discontinuous? Would it be possible for there to be a piecewise defined function that was continuous? I mean, the answer is yes, certainly. You can imagine, configuring a piecewise defined function where at the breakpoints, I kind of call these breakpoints, like, the filled in circle somehow overlap with the closed circle. And you may have something like with little corners on it, okay? What I'd like you to do right now is please go ahead and on your own, and then you'll check me, okay? Sketch this piecewise defined function. Sketch. Oh, whoops, whoop, eek. I know, f of x equals, okay, yeah, let's do that. Okay, -1 provides, and then f of x equals, and that's it. Let's just have 2 pieces for this, okay? Okay, go ahead and sketch this function. Let's see how we do. And then I'll ask you some follow-up questions. So pause me now and see if you can sketch this function, then come back and talk to me. All right, here it is. Look at that lovely thing. So what's interesting here is, the open circle for the horizontal line at -1 is then plugged up by the closed circle for the curve y equals cos x starting at pi. So really, I mean, I did this circle to emphasize that fact, but there wouldn't necessarily be a bulbous thing there. It would just be a doink. Uh-oh. Oh, yeah, come on. Okay. There you go. All right. And then notice also that at 3 pi, right, x is not inclusive. And if I were to ask you for the domain here, boys and girls, the domain here would be values of x less than 3 pi. What would the range be? Go ahead and tell me the range. What would the range be? What could y be? Okay, yes, y could only exist between -1 and 1. As a matter of fact, let's scroll back. Tell me the domain and range of this picture here. Okay, what would the domain and range be here? Well, actually, I think we already did the domain. Yes, we did. What would the range be of this function here? Okay, the range here would be the following. All right, notice that the range, y could be values of y equals 6 or greater. For values of y equals 6 or bigger, that accounts for this piece and this piece. But then y could be +1 or less until you get to -15 inclusive. So the way you write all that is you do the following. You say y could be, okay, between, greater than or equal to 6. Also, y is between -15 and 1. Okay, that's how you describe the range here. All right. All right, so that is it. So this concludes this screencast. What you are to then do after the screencast, again, if you follow the order of my directions, I give you that order of directions very clearly, is to do the first attached handout that's on applications of trig functions that involves displaying a word problem using a sinusoidal function, and then it asks you to generate the equation. Then you are to watch this screencast on piecewise defined functions, and then you are to do the handout that is in the resources folder in the handouts subfolder, and it's all caps. It says piecewise on it, and then do that, okay? And I will see you on Thursday. Bye.